My name is Ben Levitt. I'm a second-year SDM student here at Sloan. I've got the pleasure today to introduce Peter Carr, who will be speaking about automatically broadcasting live sports using robotic cameras. So, Peter.
Thanks, Ben. So today it's my pleasure to be able to talk to you about what could be an evolution of sports broadcasting, and that's the integration of computer vision, machine learning, and robotic cameras into the broadcasting process. So currently, for a professional sports broadcast, several production trucks will usually roll in, filled with lots of equipment and talented crew to put together an incredible broadcast to tell the story that takes place on the field or the sporting venue. The problem, though, is that these trucks can't go everywhere. At Carnegie Mellon, where our research lab is located, for instance, the gym doesn't have the facility to bring one of these production trucks in, as much as they'd love to see that happen. As a result, anything that goes on in this gym, if you want to see it, you have to be there to see the events happening live. But recently, however, though, that's starting to change. There's been some new technology with the digital video, as well as the broadband internet connections, and finally the hardware encoders that can essentially allow anyone with their camera to set up and have a live stream running in practically no time at all. Now, although the technology has solved the distribution side of broadcasting, the problem with these events, or covering the events in this fashion, is that it still looks like a small production. It's not like there was a broadcast truck there. You're lucky, actually, if you have a camera operator there. Sometimes they come in, set up the equipment, and then walk away and come back at the end of the game to tear everything down. And so we'd like to solve the problem of the production quality and essentially make it look like these production trucks could come to CMU, but yet keep the same small footprint that exists with the new technology to be able to essentially broadcast out of a backpack. And so I'm going to be talking today about what we're calling smart venues. For instance, here in the gym at CMU, we have cameras which track the players automatically. And then using that player information, the computers can then drive the robotic cameras to have multiple cameras cover the game and make it look like there's an entire production crew present to cover some of these small market games. So here's a fairly simple schematic of what goes into a broadcast. You've got the sports action, you have the camera operators covering that action, we have the statisticians, the replay operators, and the graphics operators, as well as commentators and the audio production, all going together towards the director and the producer, who eventually call which cameras go to air and then help guide the story. In this talk, we're going to simplify everything, and we're going to focus on the camera operators and on the job of the director. So the camera operators typically have their, at least for robotic cameras, would have their screen showing what the camera's seeing, and then a joystick to be able to control that camera. And the director, of course, is presented with that video wall of all the cameras that they see, and then deciding which camera actually goes to air. And so in the case of Carnegie Mellon, where you might send a single person to cover the event, we first started thinking, well, obviously you could have one person sit in front with a joystick and control the camera, but would they be able to control multiple cameras simultaneously, and could they also do the job of the director with that video wall? And we thought of this in terms of the one-man band, much like this talented musician who can come up with an interface to essentially put all of these different instruments together such that you can play them all simultaneously. What's the interface that you'd need for a single-person production crew to be able to operate multiple cameras as well as switch between them? So obviously, if we came down to the skeleton of a three-person crew, essentially two camera operators and one director, then the standard equipment works just fine. And that is that we can give a joystick and a viewfinder to each of the camera operators, the video wall and the video switcher to the director. So we toyed with the idea of, okay, well, let's just send one person in and give them maybe their right hand does camera one, their left hand does camera two, and maybe they use their feet for the video switcher. We weren't really sure, but it didn't seem promising. And so instead we came up with our interface, which we call one-man band, which is essentially a periphery view of what those robotic cameras might be able to see, the viewfinder of that camera, and then tying everything together in a touchscreen interface, allowing you to control which camera you want to actually show and broadcast to air. So here we are in the CMU gym, and here are our two robotic cameras placed up on the side of the wall. And so each of these cameras is essentially the game camera, which would shoot wide to cover the action, as well as an ISO camera, which could focus in on a particular player to help tell some of the details of that story. And in addition to our two broadcast cameras, we have a third fisheye camera in between, which essentially gives you the context or the periphery of what you would see if you were actually standing behind those cameras. So much like the professional operators who can stand back and, from their viewfinder and use their periphery vision to follow the action on the full basketball court, in this case, you can see the entire basketball court from that vantage point. And because we display it on a touch screen, that means wherever we actually touch on the screen, we can drive those cameras to look at that location. And so the idea to incorporate direction as well is that one finger means you want the game camera, and two fingers means you want a close-up with the ISO camera. So let's see the whole thing in action now. The broadcast output is in the bottom left corner, and right now Eric's on a close-up with the ISO camera of the player dribbling the ball up, and then can quickly switch to the game camera to follow the action now at a much wider view to get the tactical setup of how the team's going to try and score. Again, when something interesting happens, we can zoom in to get a much better view of that action, and then drop back to the game camera to again start looking at the strategic aspect of this play. Now, as I said, sometimes with these small productions, there's actually no one behind the camera. You simply go in, set everything up, lock off the tripod, and then come back at the end of the game. And so taking one-man band one step further, and that is, let's get rid of the one-man band, and let's just replace everything with computers. And for the remainder of the talk, I'm going to focus essentially how we got computers to become camera operators. Now, you can think of the computer essentially as someone who's never done camera operation before. So how would you describe, given the task of coming in and possibly never even seeing basketball before, film the game? Well, it's pretty simple. Follow the bouncing ball. That's generally what we'd tell someone. And we started looking at the literature to figure out, well, what have other people done in camera control? And unfortunately, there wasn't a lot to look at. There's maybe a handful of papers that have looked at robotic camera control, especially in the applications of sports or broadcasting in general. But then we changed it a bit, and we said, well, what if it's follow the enemy target? Well, it turns out there's a huge amount of literature on this topic already, and people are really good at being able to solve this task. And the standard method that's used is visual servoing, and here's a clip that most of you probably recognize. If we had sound. Unfortunately, we don't. So there's Darth Vader going after the rebel fighters. And hopefully you can see the similarities of Darth Vader trying to maneuver his spacecraft to keep that enemy target dead in sights. And that's exactly what the camera operators need to do as well, following the enemy ball, essentially moving their camera to keep that ball right in the center of the screen. But unfortunately, that's not really what camera operation is. Camera operators are anticipating what's going on in the game, and they're framing their shots to give you an idea of how the story is actually unfolding, or essentially how the tactics of a team are unfolding to try and score. Let me give you a better idea of what that actually means. Here we've got a clip of field hockey. This player has possession of the ball. The ball's not in the middle of the screen. It's actually off to one side. Essentially, 2/3 of the space is reserved for where the action's going. And as soon as something happens, like a turnover, you can see just how quickly the camera operators reframe so that the majority of the space is showing where the action is about to go. It's not keeping the ball in the center of the screen, but essentially allowing the viewers to follow along with the play and see where the potential passes might go. Now, I guess the other side, of course, with prediction and with anticipation, is sometimes it's not clear exactly what's happened. In this case, this player has the puck, and he's going to get pressure from one player who actually isn't on screen right now, and the other player in white you see is going to take away the passing option, essentially going forwards along the ice. And so this player who's about to be put under pressure can either pass the puck to his defensive partner, or he can chip the puck up the boards to the winger. And as you see, the camera operator guesses wrong and probably panics, and then eventually is able to locate the puck again and follow the play. And so in thinking about those two examples, and then trying to define what is the task of camera operation if it's not simply following the bouncing ball, we decided to sort of formulate this in terms of it has to be smooth and purposeful motion. We don't want the camera to jump all over the place, and much like the previous example you saw, we don't want the camera to look as if it lost the play and couldn't understand what was about to happen next. So there's a very big difference between having smooth motion and then having purposeful motion. So now coming back to Carnegie Mellon, this is our setup that we have now with two cameras on the ceiling. These are essentially our machine vision cameras, which are able to track all the players on the basketball court live. And then down below, we have 3 broadcast cameras, so we can essentially run 3 different camera operation algorithms simultaneously to see which one is actually giving us the best broadcast. And so here's what we see out of our machine vision camera. So at every frame, the computer is essentially detecting players and then computing their XY locations. And what's critical in order for a robotic application to actually work is to get the latency down to essentially 0. And so in this case, we're down to a single frame, meaning that within about 30 milliseconds of something happening on the basketball court, we know, at least in the computer's capabilities, it understands the XY locations of those players on the court. And so our baseline implementation is essentially taking that visual servoing technique that we saw before for following the enemy target. So we have our detections with our 2 machine vision cameras running, and for the initial implementation, we basically just follow the centroid of all the players. And so that gives us a very coarse idea, a noisy signal, essentially of where the camera should be looking at any time instant. And we can clean that up by putting on your favorite low-pass causal filter. So essentially taking a look at all previous locations up till now, we can then smooth out that signal and compute a much more smooth camera operation to drive the robotic controller. And so then we feed that to our robotic motors, and we're able to capture an image of the action such as that below. And this, of course, is the visual servoing technique, essentially the same as what Darth Vader does to keep his Rebel Y-wings in his sights. But in our proposed implementation, I told you that camera operators don't follow the bouncing ball. They're anticipating and they're framing their shots. And so we want to try and mimic that same ability by changing this framework. And so we get rid of our causal filter. We want to replace it with a non-causal filter, which is a fancy way of saying we want to be able to predict into the future what's going to happen. And with that knowledge of how we expect the game to unfold, we can come up with a different filtering technique that actually reflects how a camera operator would use the camera. And so that means that when we see jitter in the signal, because the players are moving the ball around in the offensive court, trying to essentially get their shooter open, then we can hold the camera steady. But when it's time to actually transition from one side of the court to the other, we can ease into that motion. The problem, of course, is that with our system, we can't do perfect tracking in real time, and so we don't have a good chance of being able to do perfect prediction in real time as well. And so instead of using a non-causal filter, we essentially induce a delay, which allows the computer to see into the future. And so now our non-causal filter, when we induce that delay, becomes a causal one. The problem, however, though, is we can't feed that to our robotic controller. Essentially, if we put in a 1-second delay, I'm now trying to tell the robotic camera where it should have looked 1 second ago. But of course, I have to tell that camera where it should be looking right now. And so in addition to delaying our XY position data, we also delay our video stream. And we have now a virtual camera. And so that says that given the frame that you see down here, I'll put that into a video buffer for, say, 1 second. And now, knowing how all the players have moved in the next 1 second, we come back and say, knowing how the players would have moved in the future, how would I have framed that shot with my camera, knowing perfect information about the future? And so with the virtual camera, we can go back and we can actually synthesize what we would have wanted to do with our robotic camera using that video data. Now finally, the last thing is that we want to keep that virtual camera in the middle. That's where it essentially has the most freedom to correct for anything that might happen in the future as we're trying to anticipate what's going on in the game. And so we have additional feedback which essentially kicks the robotic camera. Every time the virtual camera starts to drift one way or the other, we then crank up the gains on our robotic camera to try and keep that virtual camera in the middle so that we're always in the most stable position to counteract what we think is going to happen versus what actually happened. So here's our robotic camera running live, making decisions in real time, and we shoot wider than we need to be. And then inset is the virtual camera running on a 1-second delay. And so as the camera moves from left to right, you'll see the virtual camera essentially sliding around within the frame. It's basically smoothing out that jittery robotic motion that we expect to get when we're making all our decisions live, and it's able to then look at how is the play unfolding and change the filtering technique so that it knows when to hold the shot steady and when to make the shot move smoothly. Whereas visual servoing, essentially always trying to react with 0 latency, is constantly jittering, trying to decide, are the players actually all moving to one side of the court, or is it simply just the players shuffling around and trying to react to it? Now at the end here, you can see one of the problems is that we get black pixels coming in. Essentially what happened there is that the camera, the real-time algorithm to drive the robotic camera, drifted away from where the virtual camera wanted to look. And so that's a bit of a design choice. You could either lock your virtual camera to always stay where the robotic camera was looking, and you'll never get black pixels, or we can allow those solutions to diverge on occasion, which means we then incorporate black pixels into our final output. So in conclusion, smart venues could be an evolution of sports broadcasting. Essentially, we're taking computer vision to sense what's going on within the environment, and we're using machine learning to then take that sensory data and actually formulate an understanding of what we think is going on within the game. And then finally, we have robotic planning and control, which is then deciding what are the appropriate actions to take given our understanding of the game and making sure that we can actually carry those actions out. And so possibly in the near future, if you keep making all the big plays in your lunchtime basketball league, perhaps you'll be able to become famous, as the world may soon be able to watch all of your pickup games. Thanks very much.
So let's start with some questions. If you have a question, you can come up here if you'd like, or I can bring the mic over. So any questions?
Sure. Quick question. So are y'all looking at using this yourselves, obviously, for broadcast purposes, but also when you look at Division III, Division I, facilities that use some of their own inexpensive measures, is this going to scale down to that ability where these schools could purchase this kind of package, or are y'all just looking for full production value?
At this point, I'd say it's more a prototype of what are these technologies capable of. For Disney Research, we try not to think too much about what the end applications of it may be. We really do try to figure out what is state-of-the-art computer vision, what is state-of-the-art machine learning. Certainly at this conference, right, a lot of the work is done in terms of an offline approach afterwards. And so some of the machine learning we do is offline to essentially teach the computer how basketball works. But in this case too, there's a whole new set of applications that open up if we can get real-time performance and essentially zero latency performance coming out. And so doing Div 3 basketball for CMU is certainly one possible application, but there's a host of other applications as well.
Next question. I can ask a question. So what do you think the cost for this kind of technology will be available to like smaller teams, to high school teams, to other sports, like sports that probably don't create money like field hockey, things like that?
Yeah, I mean, I think if you look at what always happens with technology, right? That's something that's a prototype now. If it's popular and there's a market for it, quickly then goes into mass production and costs come down substantially. I mean, if you think at the beginning with the example of just broadcasting over the internet, right? Several years ago, that was sort of the domain of a select few who could actually afford to do that. But now it's essentially cheap that even high schools and so forth can probably buy that equipment and broadcast their games that way.
Right, so my question was how close we are to that point.
We're getting there.
So one difference between the one-man band and the robotic cameras seems to be the composition of the wide shots and the close-up shots. Mm-hmm. Do you think the technology is going to the sort of in the future where the robot will be able to sort of understand when you should have the wide shots and when you should have the close-up shots?
Yeah, so we've started to look at that question. There's two aspects to it. To some degree, there's the directing problem of what shot do you call at the appropriate time. And to some degree, there are certain patterns to that. There's also a certain style that each director has their way of choosing shots to tell a particular story. The main challenge is essentially looking at what can we get in real time and how good does that signal need to be. So to drive the game camera, I don't need perfect tracking of all the players, because if I lose somebody for half a second, we can reacquire them later on, that's fine. We have enough players, and looking at the average, the game camera is good. If I wanted a close-up on each player, now the need for perfect tracking gets a lot higher. And it may not be that I have to have identity correct all the time. There's ambiguous situations. We could go to sort of a medium shot where I can at least follow 3 or 4 players. So I think as the technology improves, for the tracking side, we then have the freedom to start looking at some of the more challenging camera and broadcasting aspects.
Obviously, the system works well for basketball and soccer, but would it work well with baseball, where the players are more stationary?
I imagine it would. The player tracking technology that we have run outside. There are different things you can do. Essentially, when you go outside, you have to deal now with shadows and so forth and other more adverse lighting conditions. And you can either tailor the algorithms to let the computer understand that it's watching baseball in particular. And much the same way with all the other machine learning techniques, is there's essentially some components of the system are sport agnostic in that they should just carry over to any sport. And then I think for specific applications, there could be problems specific to baseball, which we could then tune the particular system to be capable of getting around those problems.
Yeah. Question is regarding the weather for outside sports, for rain and all this. Would this be a problem?
It's not. Actually, I think I have, yeah, I'll show you. So this is in harsh sunlight. We can generally deal with all the shadows without an issue for the most part. You get false detections on occasion, but for the most part we can filter through it. This is heavy rain at night. So again, we can pick up raindrops on occasion, but the fact that we have stadium lighting at night doesn't seem to be a problem. We can deal with camera shake in the wind. We can deal with partially overcast clouds as well. So it's a fairly robust algorithm that we're able to run in real time. And then, as I said, this is just detection. It's not actually tracking any of these players. So it shows how reliable the detection is in terms of getting the XY position. And then from there, we can do tracking and other things on top to essentially filter out some of the detection noise that we're getting.
Okay. You have another? One more.
My question was, in addition to broadcasting, where do you see this technology can be applied?
I would say anything right now that, I mean, in terms of robotic camera control, one of the popular applications recently has been lecture halls and other things like that. So again, where, it's hard to justify sending in a production crew to make, to do something more than just a camera on a tripod. But in terms of actually making archival footage that you want to then watch later on, I think any event that is suitable to video recording could potentially use technology like this.
Great, great. So thank you, Peter. Great presentation.